In this video, we're going to talk about motion along a curve. So let's begin with a definition. If r of t is the position function of a particle moving along in a curve in 2 space or 3 space, then the instantaneous velocity, or sometimes we just say velocity, instantaneous acceleration, again we just say acceleration, and instantaneous speed of the particle at time t are defined by these formulas. So the velocity, v of t, is defined to be the derivative of the position function, the derivative of rt, or another way of writing this is r prime of t. Okay, dr dt or r prime of t. The acceleration is the change in velocity, right? The rate of change of the velocity function. So a of t, the acceleration, will be dv dt, or in other words, d squared r dt squared, which is really r double prime of t. Okay, so the velocity is r prime of t, the acceleration is r double prime of t. Now notice the velocity is a vector. Okay, v of t, r of t was a vector valued function, so r prime of t will be a vector valued function. And if you plug in a particular t, then you're going to get a vector. So velocity is a vector, and same thing with acceleration. Okay, now speed, though, is the magnitude of the velocity. Okay, so the speed is the magnitude of r prime. So the speed is really just a number. Okay, so that's the difference between velocity and speed. Velocity is a vector, speed is a number. Now notice over here in this picture, so we have this green curve that's being traced out. So I have a formula, r of t is equal to this. We have this green curve being traced out, and we might wonder, what's the position or velocity or acceleration at different times t? Well, when t is 1, it turns out you're right here along the curve. So when t is 0, I think -1, that's probably when you're here. So t can't be less than -1 because of this. But when t is -1, it starts here. When t is 0, maybe it's over here. When t is 1, it's here. So the curve is being traced out this way. At this point, t equals 1, what's the velocity? So what you'd have to do is take the derivative of this and plug in 1, and you get a velocity vector pointing off in this direction. Now, again, the velocity is a vector, and notice the vector is tangent to the curve there. But actually, just looking at the original position function, that doesn't tell you exactly what the velocity will be unless you have a parameterization of the curve. So we do have this curve parameterized by this vector valued function. If the curve were being traced out more quickly, you'd have a longer tangent vector there. You'd have a longer velocity vector. If the curve were being traced out more slowly, this velocity vector will be shorter, right? The length of the velocity vector, right? The magnitude of the velocity vector, that's the speed. Or if it were being traced in the opposite direction, the velocity vector would be pointing the other direction. And by the way, the same thing would happen with the acceleration. The acceleration is going to be a vector. How the curve is being traced out, whether it's that you're speeding up as you go through that point or slowing down, or how you're going here, that's going to affect what the acceleration is. So you can't just look at the curve and see what the velocity vector is and acceleration vector is. You need some type of parameterization. Okay, now to point out a little bit more what we're talking about here, and to really emphasize that velocity is a vector, let's look at Newton's second law of motion. So this law, quantitatively, the law says this, that force is equal to mass times acceleration. Now, I guess technically force is a vector. The force is being applied in a certain direction, right? And same thing with acceleration. But you could interpret this as saying really the magnitude of the force is equal to the mass times the magnitude of the acceleration. Now, the way I think of this, and this is kind of a maybe imprecise way of thinking about it, but the way I think about it is if you experience an acceleration, you'll experience a force. So your mass usually is not changing, right? But if you experience an acceleration, so you have a non-zero A, okay, and your mass, of course, is not 0, then you'll have a non-zero F, right? If you experience an acceleration, you will experience a force, okay, and really vice versa as well. So what does this mean? And remember, what is an acceleration? Acceleration is a change in velocity, right? It's the rate of change of the velocity. Right, so notice, how could you experience an acceleration? Well, imagine driving a car down a road, right? If you're just going along at 50 miles an hour, okay, you're not changing your speed at all, you're just driving along this straight road. Notice you won't experience any pull when you're forward or backward or to the side, right? But if you speed up, right, if you hit the accelerator and you go from 30 miles an hour to 40 to 50, you'll feel that pull back in your car. And likewise, if you hit the brakes, right, you'll feel a pull going forward, right, because you're slowing down. Now, why do you experience that pull? Well, because you're accelerating, Okay, you're speeding up or slowing down, right? Decelerating. So if you experience acceleration, you'll experience that force. That's why you feel that pull forward or pull backward when you speed up or slow down. Now, notice, though, that if you go around a curve, okay, even if you're going at a constant speed, let's say 30 miles per hour, if you're going around this curve, don't you feel a pull to the outside? In fact, the sharper the curve is, the more you feel that pull to the side. Now, why do you feel that pull? Because you might think, well, I'm not accelerating at all. I'm just staying 30 miles an hour the whole time. Well, it turns out you are accelerating because, remember, acceleration is a change in velocity, and velocity is a vector. Okay, so you could change your velocity by changing the magnitude of that vector, right? The speed, that's what we were doing here, speeding up or slowing down. But you could also change the velocity by changing your direction. Okay, so instead of so right here, the velocity vector would be pointing off in this direction, whereas up here, the velocity vector would be pointing off in this direction. So even though those velocity vectors might have the same magnitude, meaning that you're driving the same speed the whole time, they're changing directions. Okay, so a change in velocity is an acceleration. So you could change your velocity by changing the direction you're going. That's why you feel that pull. Okay, so force is equal to mass times acceleration. But remember, acceleration is a change in velocity, the change in the velocity vector. Okay, now let's come back to this page here. So let's do an example. Find the velocity, speed, and acceleration of the curve r of t equals this. Okay, t, comma, 1/2 t squared, comma, 1/2 t cubed. Okay, at the time when t equals 1. So maybe at t equals 1 second, right? How fast are you moving, right? So what's your speed? What's your velocity? What's your acceleration at that time? Now, by the way, so let's write this as r of t equals t 1/2 t squared 1/3 t cubed. So I've written it in here in the bracket notation instead of the ijk. Okay, so what's your velocity? Well, your velocity is r prime of t, right? The derivative of the position function. So the derivative of t is 1. The derivative of 1/2 t squared is just 2. And the derivative of 1/3 t cubed is t squared. Okay, now your acceleration will be v prime, right? It's a change in velocity, which is really r double prime. Okay, so what's the derivative of this? Well, the derivative of 1 is 0, the derivative of t is 1, and the derivative of t squared is 2t. Okay, so we have our position, velocity, and acceleration vectors. Now, notice, though, what's r of 1? Okay, so we're trying to find what's your velocity, acceleration, and your speed when t is 1. But actually, where are you when r is 1? Well, when r is 1, you're at the point, well, plug in 1 for each of these t's here. You're at the point 1, comma, 1/2, comma, 1/3. By the way, when r is 0, I think you're at the origin. So you'd be at the origin, and this curve is going to be coming out from the origin some way like this. Okay, but where are you when t is 1? You're at the point 1, comma, 1/2, comma, 1/3. Okay, now when you are at that point, what's your velocity? What's your speed? What's your acceleration? So this is where you are. Now, how fast are you going, and what's your velocity? So when t is 1, v of 1, well, let's plug in 1 for t. You would get 1, comma, 1, comma, 1 squared. Now, 1 squared is just 1. So your velocity is just 1, 1, 1. Okay, so notice that's your velocity, and it's a vector. Now, if you wonder how fast are you going, what's your speed, that would be the magnitude of the velocity vector. So that would be the magnitude of v1. Okay, so the magnitude of 1, 1, 1 would be the square root of 1 squared plus 1 squared plus 1 squared. That's the square root of 3. Okay, so that's your speed. Now, the square root of 3 is about 1.732. So what that means is you're going about 1.732 units per second. Okay, if t is in seconds. Okay, that's how fast you're going, 1.732 units per second. Okay, now your velocity is 111. It's just the magnitude of that velocity is this speed here. Okay, and finally, what's your acceleration? Well, plug in 1 for t. Okay, so what's a of 1? Well, if we plug in 1 everywhere we see a t here, we're going to get 0, comma 1, comma 2 times 1. So it's 0, comma 1, comma 2. That's your acceleration when t is 1. And notice the acceleration is a vector. If you want to figure out, well, how much pull are you experiencing, right? If at that moment, well, what's the magnitude of the acceleration vector? Well, it'd be the square root of 0 squared plus 1 squared plus 2 squared. That would end up being the square root of 5, which is like 2 point something, right? So it'd be 2 point something, and then that would be units per second squared, right? That would be the acceleration that you're experiencing, or really the magnitude of the acceleration would be that. Okay, so that's position, velocity, and acceleration.